All right, everybody, let's get back to our infinite plane of charge. This is where we left off our last video where I derived this equation here. So what we're looking at is a large sheet of charge, essentially. And when I say infinite plane, obviously that's not really practical. You can't have an infinite plane. So in practice, it'll be like, let's say we're looking at a point here. Actually, this point here. Okay, so a point pretty close to the sheet. So a distance, let's call this D, away from the sheet. And so that distance D will be so close to the sheet compared to the size of the sheet that the sheet would seem essentially infinite. So an analogy of this, it's not a perfect analogy, but an analogy of this would be, standing on the surface of the earth. You're standing on the surface of the earth, you look down, you look kind of a few hundred feet away from you, and it looks like the ground continues, to go on forever. Of course, I'm ignoring the curvature of the earth there, but that's the idea, that you're so close to the surface that it looks like the ground extends to infinity. Well, this is kind of the same idea. We're so close to a sheet of charge here, let's say a conductor with a certain amount with a net charge on it, that it looks like an infinite sheet. So we're going to approximate it as an infinite plane of charge, and we have our equation down here, where eta is the surface charge density. Right? So eta, surface charge density here, divided by 2 epsilon 0. And remember, epsilon 0 is a permittivity of free space. That number is 8.85 times 10 to the negative 12. Okay, so we talked about this last time, and we noted that this does not have a dependence on distance. This electric field stays constant no matter how far you are from the sheet. So if I was going to draw my electric fields, let me erase this part here. So if I draw my electric fields, my electric field is coming from the sheet here, and it doesn't get weaker. It just keeps going and going, and it maintains the same magnitude. Okay, so I'm only going to include a couple of these here. I'll draw a couple more for my electric field. So I have my electric field coming from here as well. Okay, so I also have electric field in the back, right? So electric field is going the opposite direction in the back here. Okay, so that's where we left off last time. I want to put another sheet of charge here, and I'm going to make it parallel to this initial sheet. So I'm going to draw another one here. Let me draw like this. All right. All right, trying to draw it to make it pretty close to parallel at least. All right, that's good enough. All right, so let's put, in this case, I'm going to put negative charges here. So make these full of negatives. Okay, same charge density. So both plates have the same charge density, despite how I drew my charges there. So this one has a positive charge density, positive eta, and then this one on the other side here has a negative eta. So they have, let's just say they have the same charge density. Let me actually move this a little bit. Come on. So I'm just going to move this, something like that. Okay, now this negative also creates an electric field. And remember, for negative charges, electric fields point, the electric field that the negative charges create always point towards the negative charge. Whereas the positive charges, the electric field always goes away from the positive charge. And you can see that here, right? Here's positive charges, so the electric field will go away from it. Well, if we have negative charges here, my electric field will go towards it. So I have electric field here going towards my sheet here, and also over here. And it still has the same characteristics. So we're talking about an infinite sheet of charge, and so that electric field is not going to get weaker. it stays constant over space. So we're still using the same equation here, same relationship, or same same characteristics as we saw for the positive sheet. We're just applying it to the negative sheet here. Okay, so constant electric field throughout space, and even behind here, I still have my electric field from the negative charge going towards it. And behind this negative charge, to the right of this negative charge, I have electric field pointing this way. Okay. Also behind the negative charge, which I don't have drawn here, is the electric field from the positive charge. So let me also draw that. So on the right side of my negative plate here, I'm going to include the electric field from the positive charge, which will point this direction. Okay, so let's look at a couple of regions here. If we look at this region, we see the electric fields are, we have one electric field going to the left, the other electric field going to the right. Well, if I add up all the electric fields I have here, right, these two electric fields will cancel each other out. So that leaves me a net result, or a net electric field, E net, of 0 on the right side of my parallel plates here. On the left side of my parallel plates, we kind of see the same thing, right? Electric field going to the left, and another equal but opposite electric field, right, going to the right. So these two, or all these, are going to cancel each other out, and I'm left with E net equals 0. So these parallel plates here give you a 0 electric field outside of the plates, but in between them, we have two electric fields here, right? Both the red one and the blue, and they both have this equation, right? They're both following the same equation, both going in the same direction. Right? Obviously, different sources. The blue is created by the positive charge. The red electric fields are created by the negative charges, but they're both going in the same direction. And so we're going to add these up together, and this gives us a net electric field of eta over epsilon 0. Okay, so this is a parallel plate capacitor, and the reason why we call it a capacitor we'll get into later in chapter 25 is when we start looking at that. But for now, a parallel plate capacitor essentially gives us a constant electric field in between the plates given to us by this equation. Right, it's just 2 times this electric field here. So here's the electric field in the parallel plate, and I could represent this parallel plate a little differently, as something like this. Okay, so if I make my upper plate here the positive charges, and the lower plate negative, then I have, then it creates an electric field. I'm just going to draw the total electric field. So it looks like this. So I'm going to draw this as electric field lines. Remember, electric field lines are just another way of representing the electric field vectors. I think I discussed it in a previous video, so you can go back to that video and look. Okay, they're supposed to be equally spaced apart here. Okay. So just to refresh your memory, electric field lines pretty much tell us that we have an electric field going in the direction shown. The fact that they're equally spaced here, you can see equal spacing, is telling us that we have essentially constant electric field within this region. Okay, so anywhere within this region, no matter how close you are to the positive charges or negative charges, you have a constant electric field. And I am treating these as infinite planes of charge. Okay, and we can do that. That's a decent approximation if this distance here between the plates is pretty small compared to the dimensions of the plate themselves. All right, now once you get here, you know, it obviously stops being infinite. We can't treat it as infinite because it stops. But so when it stops being infinite, or when we can't use that approximation, we do get some fringing effects. So the electric field kind of bows out like this, something like that. And same thing on this side. So here's my electric field. It is gaining, you know, let me draw this one a little bit neater. Okay, so the electric field in this region here is getting weaker, and I should have probably put more spacing between here. But as you come out, electric field is kind of bowing out this way. Electric field is getting weaker here, not as strong as it was here, and not as uniform either. Okay, not as uniform. Okay, now these are called the fringing effects of a capacitor, of a parallel plate capacitor. In problems that we'll be looking at, we typically ignore this, but there is a lab coming up where we'll construct a parallel plate capacitor, or at least a simulation of that, and we will see this. We'll be able to see this fringing here. Okay. Okay. So this is how we could create a near or pretty constant, near constant, if you know, if we include this. But if we just look at the center here, we get a constant electric field. And now what I want to do with this constant electric field is put a charge in there. I'm going to throw a charge in there, and I want to see what happens to that charge as that charge is moving through this capacitor. So we're going to be looking at dynamics. So dynamics of charges in electric fields. I'll put E fields. Okay, so I'm going to start with a parallel plate capacitor, just like I had drawn. So let me sketch this out really quick. Okay, and I'm not even going to say which one's positive or negative, but so I'm just going to draw my electric fields. I mean, you should be able to tell once I draw my electric fields like this, you know, going from up to down, you know that the top charge is, the top plate is positive and the bottom plate is negative just by the direction of the electric field. Okay, so let's say, so I have this electric field, and we know it's constant. Okay, so we have a constant electric field, and of course we could even calculate what that is, right? We have the equation for that electric field is eta over epsilon 0. Okay, so we would need to know the charge densities there on the upper plate and bottom plate. Okay, so given that we have this constant electric field, let's take a negative charge, and I'm going to give this charge an initial velocity here. Okay, we'll call this V for now. Initial velocity. Now, as it goes, kind of my first question here that I want to analyze this with. First question, as it goes into this parallel plate capacitor, what's going to be the trajectory? How is the path going to look? Is it going to just go straight? Will it curve? And if it curves, will it curve downward, upward? You know, what direction will this go? Will it just go down? You know, what does this look like? And in order to answer that, let's put that negative charge in the electric field itself. So once it enters the electric field, there you go, what direction will it have a force? Okay, what direction will the force be acting on it? Now, we are going to ignore gravity. Typically, gravitational effects are pretty small. I mean, if this was an electron, if you think about the mass of electron, it's 9.11 times 10 to the negative 31, right, kilograms. So gravity is typically, you know, I mean, multiply that by 9.8 is not a lot. It's still 10 to the negative 30. So it's not a lot. So gravitational forces are typically ignored. You do want to look out for the situations where gravity is implied. There's a couple of questions in the homework where you have like a charge hanging by a rope or something, or you want to levitate something. So if the question says levitate, yeah, you want to counter gravitational forces, but typically we ignore gravitational forces just because they're so small. So let me erase this here. Okay, So ignoring gravitational forces, what direction do we have the electric force acting on this charge? What direction is electric force going on this charge? So remember, electric force is QE. Okay, so according to this equation, F, your force, will go in the same direction as E, only if Q is positive though. Now, if Q is a positive charge, then F and E will go in the same direction. If Q is a negative charge, like we have here, that means F will go in the opposite direction as E, right? Because this Q will introduce a negative into our equation here. Okay, so in this case, if my electric field, here, the black is my electric field here. Okay, here's my electric field. If electric field is going down, what direction will the force go? Well, because it's a negative charge, force will go in the opposite direction. So I'll draw force going like this. Okay, so this is force. All right. So we know it's pointing upward. So that means as this charge, let me draw the trajectory here. As this charge goes into the capacitor, we have here's a path. It enters the capacitor, force starts acting on it, and we're going to start to see a curve, right? It starts to go up towards towards a positive plate. And that kind of makes sense, right? A negative charge would be attracted to the positive side of the plate here. So we expect that kind of curvature. All right, so if we want to do a little bit more analysis on this, not just see what kind of curvature it is, but what if the problem said, what was the distance it travels into the capacitor before crashing, or how long did it take for this charge to crash on there? How do we analyze that? So we need to know a couple things. First of all, when we're talking about dynamics, especially something like that, we have constant electric field, we're going to need to know acceleration. And we could find acceleration through Newton's second law. F net equals ma. Okay, now in this case, what's our net force? Well, a net force is only this force here, this upward force. This is our electric force here. Okay, so when we talk about F net, I'm really looking at QE. That's our F net, our force, equals ma. All right, and we solve for this. A equals QE over m. Okay, you just have to be careful because if you think about vectors here, you're gonna put a negative there, or I guess the negative is in the Q. So I guess we don't have to put that there. So just Q would be negative. That indicates that our acceleration is going upwards, right? So we do expect an upwards acceleration here. Okay, so we have our acceleration here. Here's our acceleration. This will be in our y direction, ay. Oops. Now that would not affect this initial velocity, right? This velocity is horizontal, whereas the acceleration is vertical. So this charge, as it moves forward, maintains this horizontal velocity. Let me call that velocity Vx. Vx here. So that Vx is maintained. It's just that a acceleration, the ay, is going to be increasing its vertical velocity upwards. So you can think of this is just like a projectile motion problem, right? Back in your previous physics course, you looked at projectile motion and solved, let's say a ball is kicked off a cliff. How far does that ball go? This is the same situation here, except instead of the ball falling forward or falling down towards the ground, you have a negative charge moving up towards a positive plate. But it's the same general equation. So we typically look at, you can think of this as, you have the horizontal motion. and the vertical motion. Okay. For the horizontal motion, that velocity, for this problem at least, that velocity is essentially staying the same. So, you know, the only real equation that determines that is that equation for velocity, Vx equals delta x over delta t. Or I could rewrite it slightly, x final equals x initial plus Vx times delta t. Or, you know, I'm not going to write delta t. I'll just keep it as t. It's the same thing. Delta t is change in time, but if your initial time is 0, which it typically is, you know, just put it as t. All right. So that's pretty much the only equation we have going on for the horizontal motion. For the vertical motion, because you have acceleration in the vertical motion, there's no acceleration in the horizontal, right? I could even add to this ax equals 0. Right, there's no acceleration horizontally. You do have acceleration vertically. So because of that, all our kinematic equations that were from your previous physics course is going to come back. So let me write a couple of them. So we have y final equals y initial plus v initial y, which in this case would be 0 because it's not moving vertically in the initial position. T plus 1/2 ayt squared. Okay, so that's 1. Let me write this a little bit clearer. This is yf here. Then we have v final y equals v initial y plus ayt. All right, so we're thinking about components here, vertical components versus horizontal components. And then one more, v final y squared equals v initial y squared plus 2ay delta y, right? Change in y. Okay, so kinematic equations kind of come back when we're looking at this. And these equations, remember, these equations, if you don't remember, let me just tell you, these equations were derived when acceleration is constant, right? So this only works if this electric field is constant, right? Then we can think about using our kinematic equations. If this electric field is not constant, our kinematic equations won't work here. So we would have to derive new equations starting from Newton's second law, but it would be a bit more work there. Okay, so that is how we look at dynamics in charges, or dynamics of charges in electric fields. We go back to Newton's second law. Okay, now there's one more situation I want to talk about today, and that is what about a dipole in a electric field? So let me draw an electric field here. Let me label this. Okay, so let me draw these arrows here. Okay, so here's my electric field, E. Okay, and then I'm going to have a positive charge. I guess I'll do just do in black. And a negative charge. And so a dipole, usually these positive and negative charges are in some kind of molecule or in an atom or something. So the positive and negatives, they're not free charges in the sense that they're just going to be attracted to each other. They're somewhat fixed relative to each other. So I'm going to draw this. I'm going to draw almost like a rod that's connecting them to kind of model that. Oops. Do this. Oh, I thought it was going to be a little darker. Okay. So they're connected there by a rigid rod. You could think of it. So that's how I'm going to model this dipole. And this has a negative Q here. Negative Q, and we have a positive Q. Okay. Now, these two charges are in electric fields. So remember we saw that when you put charges in an electric field, you're going to get a force, right? F equals QE. And the direction of force kind of depends on the polarity or the, yeah, I guess polarity of the charge, the sign of the charge. If it's a positive charge, force will go in the same direction as the electric field. So if we're looking here, this positive charge, I would draw the force going in the same direction as the electric field. So something like this. Force. This negative charge down here is in the same electric field. So this E is the same as this E. We're looking at a constant electric field here. Okay, maybe perhaps this constant electric field is created by a parallel plate, you know, or something like that. So this negative charge is feeling the same electric field, but because it's negative, that force will go in the opposite direction. Okay, but it's equal and opposite there. This force here and this force here are equal and opposite. Okay, so what's going to happen? Well, forces are equal and opposite, so my net force is 0. Right? I do not have a net force here. But what I do have is a torque. Right? You could kind of think of it if this is, you have these two charges here, feeling these forces, well, it's going to start to rotate around the center of mass. Let me put my center of mass here. I'll call this the center of mass right here. Oh, you know what? I forgot to call my total distance here. The distance between the two dipoles. Here is D. Okay. All right, so it's going to start rotating around this center of mass, which the center of mass, because I'm assuming the two charges, I guess, have equal mass there. So this the center of mass, which is be at D over 2, right? And just cut that rod in half, and that's where your center of mass is. So you get two torques. You get a torque from the positive plate. So a torque on the positive plate, and you get a torque from the negative plate. So I'm going to add these together. Now those two torques are essentially have the same. They're both both going in the same direction, right? This torque here from that this force is creating is going to cause this positive charge to go in a clockwise direction. This force creates a torque that will cause this negative charge to go also in a clockwise direction. So we're going to see this overall clockwise direction here. So these two torques are complementing each other. Actually, we say in the first physics class here that if you get a torque causing a clockwise rotation, we say that's a negative torque technically. Okay, so that would technically be a negative torque, but I just want to calculate the magnitude of the torque here. Okay, so so this will give me our total torque. I want to find out what these torques are. So let me just focus on T plus for now. Well, remember torque is found like this, right? R cross F. So R is the distance, just to refresh your memory here. It's not just distance, it's really a vector, it's a position vector that points from the axis, or in this case the center of mass, to the location of the force. Okay. So in that case, what are we looking at here? So for R, we're looking at this position from the pivot, right, which is my axis here from the center of mass to the location of the force, right here. So we're looking at this distance here. So let me represent that, and it is a vector. Right, you can see the r vector there. So my r vector will look like this. Okay, that's my r vector. Well, my r vector is just d over 2, right? It's just half of that. So r vector would be d over 2, and it's still a vector. So if you look back when I talked about dipoles, I believe that I defined the dipole as pointing from the negative to the positive. So this is actually, the d vector here. And it actually makes sense with what r hat is, right? R vector, it's not r hat. This r vector here. Go back to blue. Right, it goes from the axis to the positive charge. So that's what that direction is pointing. Okay, cross F. Well, what's F? F is from the electric field. Right, so I'm going to plug this in for F. I'm going to plug this equation in. So I get cross product. Oh, I want it black. Cross product QE. Okay. Now, what about this one down here? The torque caused by the negative charge. Well, the charge is an equal distance from the axis, right? So same distance here, and we get the same direction, right? Clockwise. So the torque from the negative charge is equal to the torque from the positive charge. These two are the same torques. So I could rewrite this as just 2 torque positive. Right? They both apply the same torque. So all I'm going to do here is plug this in for my torque here. So I'm going to go 2 times d over 2 cross product QE. Okay, and I could simplify that. The 1/2 cancel, the 2 cancels out. So this 2 and this 2 cancel out. And I'm going to let me actually move all this stuff. Give me a little bit more space here. Okay, so I'm going to rewrite this. So this Q here is a scalar, right? So I can move, if I have a cross product here, I can move the scalar wherever I want. It's just, cross product is a product, so we're multiplying. So I'm going to move the scalar to the QD. So QD, I'll show you why in a second. Cross product E. And we saw that QD, when you do that, charge times distance times the distance between the two charges, that is a dipole moment, right? We defined that in an earlier video as a dipole moment. So torque, total torque on the dipole. Torque on a dipole, right, on the positive and negative charge together, is my dipole moment P cross product E. Okay, so that's the torque on a dipole moment. Now in practice, we could if you remember, we could represent the cross product a little differently. If we want to find the magnitude of torque, all you do is take the magnitude of the dipole moment times the magnitude of E times sine theta, where sine theta, the theta is the angle between the dipole moment and the electric field. Okay, so we put a dipole in a constant electric field. What we're going to see is a rotation. Now, as this rotates, I wish I could make this picture rotate without erasing things. But as this rotates, once it gets down here, the torque changes. So what you might see is, depending on the initial conditions, is an oscillation, right? An oscillation here. Because once this positive goes below, below this line here, goes down here, and once this negative goes up here, the direction of torque is going to be the opposite direction. It's going to be a counterclockwise torque instead of that clockwise. So you eventually would see that oscillation. But I'm just interested in calculating the torque acting on this dipole. So this is it right there. All right. So that brings us to the end of chapter 23. So we just kind of saw what is the effect of the electric field, but chapter 23 introduced us to a lot as far as being able to solve for electric fields from different charge distributions. Chapter 24 is going to give us yet another tool to solve for electric fields, and that's where Gauss's law comes in. So Gauss's law is going to be our focus for the next few lectures as we continue chapter 24 next time.